Now that we've looked at the basic architecture of the Android system, let's look at defensive mechanisms for Android applications. We want to understand the security features of the Android operating system, discuss data encryption and key management, and understand the basics of the code signing process. We'll discuss a sandbox, the notion of a sandbox, data encryption, key management, address space layout randomization to defend against buffer overflow vulnerabilities, an item in the hardware present on some Android phones called the secure element, the concept of input validation, and code signing. A sandbox is a term in computer security that refers to a boundary around a program. In the Android system, programs are written in Java and execute within a Java virtual machine called the Dalvik virtual machine. Each program runs in its own dedicated virtual machine and is isolated from other programs, effectively operating inside its own sandbox. Now, the metaphor of a sandbox is a simple one. We take our children and place them in a box of soft sand, and we give them a set of known safe toys to play with. The bad things on the outside world can't come into the sandbox, and the child can't easily escape. So we limit its access to bad things, we put only safe tools inside for him to play with, and we thus provide security and safety for our children. A sandbox in software does much the same thing. The sandbox is defined in the Android system by the APK and its boundary. We review the manifest.xml file that controls what can and cannot reach outside the sandbox. So review and control of those access and permissions is key. The kernel enforces these sandbox access controls and permissions defined in the Android manifest.xml file through the IPC mechanism called the binder. The application can, but should not, be coded to access resources outside the sandbox. Stay in the sandbox. That's safe operating procedure. Data at rest and data in transit must be protected through encryption. Assume the device will be lost or stolen, and the attacker will have access to the device's memory or removable memory. Data at rest requires file encryption. Data in transit requires securing and encrypting through SSL or TLS, discussed in a later module. This must be programmed in by the application programmer. It is not automatically performed in the current version of the Android operating system. It must be explicitly done by the programmer. Android provides good cryptographic libraries as components of the operating system. These include crypto, crypto.interfaces, security, and security.cert. Documentation for these is contained on the Android developers website. Key management is critical for symmetrical encipherment. And Kerckhoffs's principle from 1883 states that the strength of a crypto system depends entirely on the key, not the algorithm. In other words, I can publish the encryption algorithm, teach you how to encrypt and decrypt, but if you do not have the key, if I properly manage the creation, distribution, protection, storage, and validation of the key, then my system will be secure. This is the hardest problem in cryptography, but it's a logistical problem, a systems engineering problem, not a mathematical or cryptographic problem. Never, ever, ever try to invent your own cryptography. Use known crypto methods, use provided cryptographic libraries, and use them correctly. Address space layout randomization provides some protection against buffer overflow vulnerabilities. ASLR refers to the way the program is loaded into memory. Without address space layout randomization, each time a program is loaded into memory, the program components will go in predictable memory locations. With ASLR, that layout is randomized, so the program never goes into memory twice. When an attacker attempts to exploit a buffer overflow by writing more bytes than are allocated for a specific buffer, it will go into random portions of memory, and he will not easily be able to predict where his malicious code goes in the memory as it's allocated. ASLR has been part of Android since version 4 and 4.1 of the operating system, and references on the details of ASLR are at the bottom of the slide. The secure element is a hardware component present in some Android and other phones. It's an option for higher assurance storage of critical pieces of data, specifically authentication, credentials, or keys. It runs in a physically separate, segregated piece of hardware with a separate and segregated operating system independent from the phone operating system, typically a Java Card OS or something similar to it. It implements firewall rules to restrict access to the application protocol data unit so that only under restricted circumstances can that protected credential be retrieved and utilized by other components of the system. Data is written to the secure element through the Trusted Services Manager, an infrastructure component which communicates with the secure element either directly or through a proxy. In our case, with a mobile application, a mobile device, the proxy would be one of the carriers, the cellular phone carriers that actually supports the telephone device. All input should be validated. One of our OWASP top 10 is making security decisions through untrusted inputs. Validate input. For example, there should be no reason for a SQL command, a structured query language command, to appear within the login or password field of an application. So we test for this and validate input. Input validation follows two broad approaches, whitelisting and blacklisting. With whitelisting, we have a known list of good, trusted input data. All data input is checked against the known list, and if it appears there as known good data, it's allowed and processed. Blacklisting works in the other direction. We have a known list of bad input. We test input against the bad list. If it's there, if it matches, we do not proceed, we do not process it. In practice, whitelisting and blacklisting are often combined. All application code on the Android system, and for that matter, the other operating systems under our consideration, must be digitally signed. The mechanism is to obtain a digital certificate or a signing key from either a public certificate authority or to generate your own using something like the OpenSSL library. The application is compiled in release mode and then signed. This is the command line to sign an application with the private key. And then finally we run Zip-Align in the Android software development kit for performance optimization and to reduce the RAM usage. All Android applications must be signed, and that signature provides part of the boundary for the soundbox discussed earlier. At this point in time, Google and the Android team do not require a specific central certificate authority, so self-signatures are allowed. This means as the end user, you have very weak assurance as to the identity of the software developer or author of the application. Thank you.